Thank all of you for joining us this morning for the second installment of the webinars on the roads and airfields constructed on permafrost, a synthesis of practice. Today, we're going to be talking about thermal modeling, and then we'll be talking about some of the options you have in order to build on permafrost, as well as some of the things for the maintenance and operations and the construction folks to pay attention to when they're doing the projects. If you're not already muted, I would appreciate your doing so. If you have questions, please feel free to enter them into the chats, and we'll try to get to them at the end of each chapter. And hopefully we will be able to answer all of your questions as we move forward in that. Don't hesitate to ask questions. We encourage you to do so, but with the number of people that we have on today, we just simply can't have a long dialogue with you as we'd like. But that said, if you want to get a hold of any of the authors of the synthesis, feel free to do so, and we'll be more than happy to discuss the synthesis in more detail with you. Today, we're joined by Dr. Doug Gehring, Dean Emeritus of the University of Alaska Fairbanks, the College of Engineering and Mines. Doug has been my mentor for many years when it comes to heat and mass transfer, especially in the area of permafrost. And if you look on the DOT website, you'll find a number of publications by Doug to talking about heat and mass transfer in the soils. Also, those of you who don't know, he held a patent for a number of years on the air convection embankment. So he's the guy to talk to if you want some additional information on those. As I say, his expertise is somewhat unique in the area of heat and mass transfer. And certainly, if you have any of those issues, I encourage you to try to get a hold of him and have that discussion. So with that, I'm going to turn it over to Doug, and he will be talking to you about thermal modeling, how you go about it, what to watch out for. And hopefully we won't get too far into the weeds on the technical part of it, but hopefully we can provide you with enough information to provide you some guidance, when to use it, how to use it, and what to watch out for. So with that, Doug, I'm going to take my pretty face off of this thing and turn it over to you.
All right. Well, thanks, Billy. I appreciate the introduction. Just to add to that a little bit, I'd be remiss if I didn't also mention John Zarling, who was one of my mentors back in the 80s and early 90s when I came back here to be a young professor in mechanical engineering at UAF. But I grew up in Alaska, so I grew up driving on roads around Fairbanks and was, intimately familiar with the problems that we have with frost heave and permafrost degradation, and was quite interested in permafrost. And so with that, it'll be hard for me to stay out of the weeds. Billy is aware of that. But my intention today is to go quickly through chapter 4 of the synthesis report and try to give you an overview of the basic heat transfer that is helpful to be aware of what the mechanisms are that are important. A little bit about the different types of modeling techniques that are out there, when they might be appropriate, and probably finish up with a discussion of the most complex version of a modeling study that you might do, which would involve, of course, numerical models of one sort or another. So with that, let me see if I can share the screen here.
Some leeway.
So hopefully everyone can see that PowerPoint presentation. If not, Billy, let me know. And I'm going to probably mute my camera here while I'm talking and move forward with this. So you'll see the title is a little bit different from what Billy had. It's not the same as the synthesis title. That really is an outcome of my focus on trying to mitigate impacts of permafrost thawing on linear structures. But again, what I'm dealing with here is the version of the synthesis chapter that you have on thermal modeling. So let me try to move forward here if I can get this thing to work. So I'll start today with a little bit of an overview of thermal modeling, physical processes, heat transfer modes, and how we use those heat transfer balances to come up with equations. Talk a little bit about the physical domain, which is important from the perspective of determining what type of model is appropriate and how to go about modeling it, and talk a little bit about the time domain. In other words, if you're trying to simulate something or model something, what kind of appropriate timescales are there that you need to be concerned with. Then we'll move on to data requirements. And again, this is important from the designer's perspective, because you can't send a consultant off to do a bunch of modeling without the appropriate background information. And sometimes that can take quite a bit of effort to acquire. Both material properties and meteorological data may be needed if you want to do a comprehensive modeling study of a particular site or a particular portion of the roadway that you're designing. And then we'll talk about a couple different versions of modeling that are available, starting with some analytical modeling, which may be appropriate for some simple analyses, including the basics of the Stefan and whiplash curve solutions, and then really one method that has been a standard that DOT has used in the past anyway, was known as the modified Bergeron method. I'll talk just a little bit about the background there. And then we'll move on to numerical modeling, both 1D, 2D. I won't talk much about 3D models, other than when they might be appropriate, although those are typically difficult to complete and very time consuming. Talk a little bit about modeling advection or convection, such as occurs when you have groundwater movement, or particularly air movement in an ACE embankment that Billy mentioned in the introduction. And then questions about verifying software results and resolution, and mention briefly some commercial software that has been looked at. And then finally, some real world challenges, materials and uncertainty in boundary conditions and initial conditions. So a quick background in terms of thermal modeling. These are the three fundamental physical processes that one has to be concerned with when modeling heat transfer in a roadway embankment type situation. Typically, heat transfer in soil and gravel systems is typically dominated by thermal conduction. And exceptions do occur, as I mentioned briefly in the last slide, when you have a moving fluid like pore water or potentially pore air in the case of an ACE embankment, and that can complicate the modeling tremendously. Most of the simple methods and most simple numerical codes typically use thermal conduction as the primary heat transfer mechanism in soils and sands and gravels, and that's largely acceptable and accurate. Again, accepting only those conditions when you have some sort of a moving fluid that you have to deal with. In addition to thermal conduction, there are two other fundamental heat transfer mechanisms that have an impact, and that is thermal convection at a surface and also thermal radiation. In this slide, the convection and radiation terms are really, the context of these is really as a surface interaction. So for instance, in the case of thermal convection, the simple law that's listed there is known as Newton's law of cooling. And it simply says that Q, which is the heat flux, is a function of the temperature difference between maybe the air, which would be TA, and the surface temperature, which might be the asphalt surface temperature. And the delta T and the Q are connected by a heat transfer coefficient, which has to be looked up, and it's a function of wind speed and a number of other things. So this type of convection equation is able to account for sort of cooling because of a cool wind blowing over the surface of asphalt, for instance. Going back to thermal conduction for a second, again, Q here is the heat transfer, the heat flux vector, and it's actually a vector. What Fourier's law of conduction says is that heat goes from hot places to cold places. Well, the hot place to cold place part of that is governed by the the gradient, the temperature gradient, which is that the last term in that first, I don't know if you can see my arrow, the temperature gradient here, a heat conduction for the material. And if you use those two, you get a vector equation which tells you that the heat is moving in a certain direction. Typically in soils problems, we're only concerned with the depth direction. And so this is a simplified version of Fourier's law that's applicable in, let's say, the z direction, where z might be depth 0 at the surface and increasing downward. The third heat transfer mode, which is in many ways the most interesting, has to do with radiation. And this is also primarily a surface effect. So radiation is a result of something known as the Stefan Boltzmann law. And some of you may be familiar with this, some others maybe not, but it turns out that all objects which are elevated above 0 Kelvin, 0 absolute, which is all objects, because there aren't any that are actually at 0, all objects radiate thermal radiation. And the amount of radiation that's emitted from their surfaces is a function of the absolute power or temperature, the absolute temperature to the 4th power. So as temperatures increase, the amount of radiation that's emitted by a surface increases dramatically. Hot objects, very hot objects like the sun, emit what's known as shortwave radiation. The radiation that's emitted has a short wavelength, whereas cooler objects, things that are at more like room temperature or environmental temperatures, emit long wave radiation. And that can be important because the way surfaces react is different depending on whether you're considering shortwave or long wave radiation. I'll have a quick slide a little bit later on and talk a little bit more about this. But in this Stefan Boltzmann law, so Q is again the radiation heat flux in this case, T is absolute temperature to the 4th power, sigma is a constant, a physical constant, and E, the epsilon here, is the emissivity. So for instance, one way to reduce radiant transfer is to reduce the emissivity, and this is essentially the essence of low E windows. A low E window is a glass with a coating that reduces the emissivity and thus reduces radiant loss through the glass, and I'm sure many of you have heard of low E windows. So that's a quick introduction to the three fundamental modes of heat transfer that is helpful to understand if you're going to dive into thermal modeling. So using those heat transfer modes, the way a model is generated is by taking some sort of a representative volume. In this case, I've just taken a 3-dimensional XYZ cube of material of some sort. You look at how much heat is flowing into and out of the X direction faces, the Y direction faces, and the Z direction faces. Again, this can also be done in 1 or 2 dimensions. You don't have to consider all 3 dimensions. But the fundamental idea here is that the change in temperature of that volume is equal to the net heat flux coming in and out of all these spaces divided by the heat capacity of the material within that volume. So if you have a material, I mean, obviously the larger the net heat flux, the larger the change in temperature is going to be. The larger the heat capacity, however, the smaller the change in temperature is going to be. So heat capacity is just the physical measure of how efficient or how effective the material is at absorbing thermal energy. So something that's really effective at absorbing thermal energy may be able to take a lot of energy without changing temperature very much. So it's sort of like a thermal battery, if you will. The ability of materials to store heat is really a function of 2 types of heat capacity. There are 2 components, a sensible heat capacity and a latent heat capacity. Sensible heat capacity is heat capacity associated with raising the temperature of the material, whereas latent heat capacity is heat capacity or energy that's associated with either melting or thawing the material. So if you have a soil, if we're considering a soil matrix here that has moisture in it, both the water and the soil particles can change their temperature. So they both have sensible heat capacity associated with them. But only the water in the matrix can freeze or thaw. So only the water, the moisture portion, has latent heat associated with it. And during the freezing and thawing process, the latent heat component is often huge compared to the sensible heat component. And so when freezing and thawing is taking place, you end up with a very high effective heat capacity because of the latent heat that's required to carry out, let's say, thawing. And as a result, the heat capacity becomes very large during thawing. And even if you have a large net heat flux, the change in temperature during thawing is minimal. In other words, thawing occurs basically at the freeze-thaw temperature of the material, water in this case, which would be 0 degrees C. So the fundamental background of modeling is that you take those heat flux relations that say Fourier's law of heat conduction, you carve out a representative volume of the material and you perform a balance on this. And that results in a set of equations that you can essentially solve for the temperature of these control volumes as time goes on. So in order to carry out the modeling process, the first thing you have to do is decide on a physical domain. So what I have here is a sort of a schematic of a typical roadway embankment with a center line geometry marked there. Depending on the result you're trying to achieve or the analysis you're trying to obtain, it may be most advantageous to conduct a simplified one-dimensional simulation. For the most part, roadways are represented by two-dimensional geometry. Typically, if you look at the importance of heat transfer in the various directions, the most important and most vigorous heat transfer occurs in the vertical direction. However, an embankment such as the one in the picture here also transfers heat laterally. And in fact, typically the soil temperatures beneath an embankment like this will be impacted to a depth that's about approximately equal to the width of the roadway prism. So there will be some two-dimensionality of temperatures, and this is partly because, for instance, the asphalt surface will have different thermal characteristics than the surrounding native ground surface. And this ends up resulting in not only vertical heat transfer in the Z direction, if you will, but also lateral heat transfer in what we might call the X direction. Typically, changes along the axis of the road are much smaller. So it's uncommon that you would have to include all three dimensions in a physical model. If you had a culvert or something like that, where you were worried about freezing and thawing, maybe a culvert would result in a situation where you might consider 3D modeling. But I would say that three-dimensional modeling can only be done with a very complex numerical model. It's a huge effort just to characterize the geometry and set up a model to do that. And so it'd be a very, very large effort. And I think that's very uncommon in terms of the types of modeling that DOT designers would want to do. In terms of the time domain, clearly temperatures change minute by minute or hour by hour, but typically what designers are concerned with is the annual behavior of, say, freezing and thawing, maybe a decadal behavior of permafrost thaw, if this is a permafrost site and one is worried about the performance of the road over, let's say, a 25-year lifetime. So typical time domains for modeling would extend from years to maybe decades, with time step sizes on the order of days, and that's generally true for numerical models. In terms of what may be appropriate or not, I mean, one example I could think of is if you're designing a project for the North Slope, you might be concerned that the embankment prism is large enough to contain the annual thaw. And so, as an example, one thing you might do is a one-dimensional study at the center line of the embankment that predicts how much annual thaw you would get at the center line of the embankment. And so long as you're certain that the thaw depth does not impact the continuous permafrost, which of course we would find on the North Slope, you can be fairly certain that any thaw is contained within the non-frost susceptible, non-thaw susceptible material within the embankment prism. So you might be able to get away sort of with a one-dimensional analysis of thaw depth at the center line of the embankment. But to complicate things and and go one step forward, clearly the thawing situation near the toe of the embankment may be more complicated because you don't have as much granular material over the top of the pre-existing permafrost layer. So if you really wanted to be careful about not having a compromised toe or accentuated thawing beneath the toe of the embankment, that may dictate some sort of a two-dimensional analysis. So that's just one example that I sort of thought about. There's a lot more discussion of appropriate timescales for modeling that's contained in the text of the chapter as well. Moving on to data requirements, there really are two classes of data requirements, and these do impact the project because this is data that's going to have to be obtained probably somehow before the design is finalized. And those include both material properties and also meteorological properties for boundary conditions. So the types of material properties that are needed primarily for soils would be thermal conductivity, sensible and latent heat capacity. And these are a function of soil type, dry density of the soil or gravel and sand, and moisture content. As one example, one of the common sources for material data was Kirsten's work in 1949, and I've just reproduced a couple of plots here. This is not for silty soils, this is for sand and gravel. And you can see that thermal conductivity here is a function of water content and dry density of the material. So if you have good information on dry density and moisture content, coming up with thermal properties is relatively straightforward. But that, again, that's something that the designer has to think about, is what types of material properties are really available. Do we need to do more sampling of the site, et cetera, because these material properties are going to be needed not only for the embankment materials, but also for the underlying foundation soil materials. And once those, the soil, the dry density and moisture contents are known, sensible and latent heat capacity calculations are relatively straightforward. The modelers can easily calculate that, so long as, again, that they have an idea of what types of materials are within the embankment prism and below the embankment prism, and what type of moisture situation you're dealing with. The other set of data requirements has to do with boundary conditions. And the most complicated boundary, of course, is the upper surface boundary. And here's where some of those heat transfer mechanisms that I mentioned earlier on play a huge role. Probably the combination of radiation is the most difficult to deal with. So as I said, hot objects generate shortwave radiation. So from the sun, we will have incoming shortwave radiation. Some of the sun's radiation may be reflected by clouds. Some of it will be reflected once it hits the surface, but quite a lot of it will be absorbed. If you have a black asphalt coating, for instance, we all know that a hot summer day will generate quite a bit of heat as the sun's shortwave radiation is absorbed by the asphalt. On the other hand, the asphalt also emits longwave radiation. So there's a complex play between incoming radiation from the sun and outgoing radiation from the surface of the roadway that results in what I will just call net radiation. So we have a net radiation term that's a balance between what's coming in from the sun and the atmosphere and what's being emitted by the surface of the road. In addition, we also have the convection term that I talked about before. For instance, if you have a lot of sunlight on a very warm day, you may have very high asphalt temperatures. But if you have a cool breeze, that wind will carry away a lot of the heat. So it may not get into the embankment or the underlying foundation soil. It may be, some of that may be carried away by the wind. And one other term that we didn't talk quite a bit about, is the evaporative term. If you have moisture on the surface, some of the energy that's coming in from the sun or other sources may go towards evaporating that moisture. And so the upper surface energy balance, which is really required if you're going to be able to calculate accurately embankment and subsurface soil temperatures, is a fairly complex balance between radiation coming in, convection being carried away, let's say by a cool wind, and any evaporative losses due to evaporation of moisture. This plays the evaporative term plays a huge role in areas where you have vegetation on the surface. So the surrounding soil surface may be highly affected if you have a damp, mossy surface, for instance. So this is quite a complex balance to perform, and in some cases it may be warranted. There are models out there, commercial models, that can handle a full energy balance like this. But again, as a designer, there's no point in considering this unless you have a full suite of meteorological data available. It's got not just air temperatures, but radiation terms, net radiometers, etc. There's quite a bit of information needed if you want to perform a full upper surface energy balance. This is probably the most accurate way to model what's going on at the surface, which of course is a very important boundary condition if you want to determine embankment and soil temperatures. But again, it also has quite a bit of data requirements associated with it. Deeper down, remember in the model domain, I showed a bunch of soil beneath the embankment. So if you're going to perform a model, you want to extend that modeling domain deep enough down into the soil layer that there's very little or zero annual temperature fluctuation. And this could be, 10 to 20 or 30 meters or more of depth. At that very bottom boundary condition, the typical boundary condition that is used is known as the geothermal heat flux boundary condition, which is about 0.06 watts per meter squared. This is the amount of heat that's essentially coming from the Earth's core. So these are a couple of the boundary condition data inputs that you would need if you wanted to do this kind of a modeling study. However, you'll find that most modelers will not, well, most of the time you won't have enough data on the surface energy balance, and most modelers will not, most of the time, the accuracy that you need will not justify trying to either gain all of that meteorological data or using it in a modeling effort. So most of the time, modelers will use a simpler surface energy balance approach known as the N-factor approach. Many of you may have heard of this. Most of the time, modeling efforts will use freezing and thawing N-factors to characterize what's going on at the surface of the ground or the surface of the embankment. I won't say a lot about these, but it's essentially, the N-factor is a way of converting air temperature conditions to surface temperature conditions. And it's done so by using an air freezing index, for instance, on the freezing side. So knowing an air freezing index, which basically is the number of degree days below freezing that the air temperature maintains, and a freezing N-factor, we can then calculate what's going on at the surface, at the upper surface of the embankment or at the upper surface of the soil. The same thing is true for the thawing season. The air thawing index, if knowing that and knowing the thawing N-factor, we can calculate what's going on at the surface. I think you can all imagine that for an asphalt surface, for instance, during the summer, because of solar input, as we discussed before, you would expect higher temperatures at the surface of an asphalt layer than you would for just the surrounding air. And for instance, if you look in this simple table here that I included as an example, the N-factor for thawing asphalt here is quoted as a range from 1.4 to 2.3. So essentially that means that the roadway surface, the asphalt surface, is somewhere from 40% to about 130% larger, higher than the air temperature, which depending on how much solar input you have is probably about right. So there are various bits of data here, just an example for freezing and thawing N-factors. This is what modelers will typically use most of the time. And again, as a designer, while this can reduce the accuracy of the results that you get in the modeling effort, it also dramatically reduces the amount of data that's required to run a model. So let's move on and talk a little bit about some simple modeling techniques. The first solution that I'll talk about, which you've all seen pictures of, is something known as the whiplash curve solution. And in this case, you have it's just a one-dimensional solution. You have the soil surface here, depth given in the Z direction here. And as the surface temperature fluctuates, warmer in the summer, colder in the winter, you get this damped curve of temperature that exponentially decays as you descend into the soil layer. You've, I think, all seen pictures of this whiplash curve. The curve extremes are contained by what are called trumpet curves. You can solve this problem mathematically so long as you ignore freezing and thawing. So there is a mathematical solution so long as freezing and thawing are not important. And the only time freezing and thawing aren't important is if there's essentially no moisture in the material. So for very, very dry materials, perhaps a dry bedrock, something like that, the whiplash curve may actually give you reasonable results in terms of annual behavior of the temperature profile. Another extreme is known as the Stefan solution. So whereas the whiplash curve solution ignores latent heat, the Stefan solution ignores sensible heat. So it essentially assumes that the material is not changing temperature, it's only freezing or thawing. And based on that assumption, you can come up with a relatively simple estimate of either the freeze or the thaw depth. And so if it's a very wet material you're dealing with, for instance, water, the Stefan solution actually can give you a pretty good estimate for instance, the depth of ice formation on a lake, because the amount of energy that's removed from the surface of the lake to the ambient air, almost all of the energy that's removed goes to creating ice. Very little of it goes to cooling off that ice. And so the Stefan solution is a pretty good solution if you have a very, very wet material or you're dealing literally with 100% water. Neither of those approximations are typically true for soils, though. Most of the time you have some water, not zero, and not 100%. And so most of the time for soil modeling or embankment modeling problems, both the latent heat and the sensible heat play an important role. There's one analytical solution known as the Neumann solution, which actually includes both of them. It's very complex mathematically, involves the use of an error function, which is a function that arrives from mathematical theory for solving these equations. And it's also relatively simple in that it assumes that the initial soil column is all at one temperature, say T0, maybe above the freezing temperature. And that at the beginning of time, we suddenly lower the surface temperature to some fixed value T surface. And as time progresses, in this case, since the surface temperature is below freezing, you get a freezing front progression with time. And the Neumann solution can actually tell you exactly what these temperature profiles look like, but only for the simple case where the surface temperature is fixed, which of course is not what we have in the real world. Typically in the real world, of course, temperatures vary from hour to hour, day to day. In the wintertime, generally they're below freezing, but they're not fixed like this. So the nice thing about the Neumann solution is that it can be used to verify numerical models that include freezing and thawing. So it's a good verification model for making sure that your numerical model is able to capture all the important parts of freezing and thawing problems. The one that's been practically used by DOT in the past, and maybe after I'm done here, Billy can chime in on whether this is still available. I know for a while DOT had a program that they called ModBerg. The modified Bergin method is essentially a layered version of the Neumann solution. It does include both sensible and latent heat, so both cooling and warming of the soil and freezing and thawing. It's used for calculating freezing or thawing depths in layered systems like you have in a roadway embankment problem, gravel, D1 gravel, silt layers, etc., maybe even an insulation layer. So it is well suited for roadway embankment problems, and it can be implemented in a spreadsheet. This would be a relatively simple modeling effort that, for instance, a modeler or consultant could do relatively quickly. If all is needed is a freezing or thawing depth analysis, and you and the modeler are convinced that the one-dimensional analysis is appropriate for the conditions. For instance, you're not worried about what was happening at the center line versus what might be happening at the toe of the embankment slope. That would probably dictate a two-dimensional analysis. Moving on to numerical modeling, and I've got just a couple more slides left here, so we're getting close to the end. Numerical models are available for 1 dimensions, 2 dimensions, and 3 dimensions. In 1 dimension, finite difference and finite element models are essentially the same for the most part. The formations may be slightly different, but they both use, in 1D, they'll use a one-dimensional grid of node points, starting at the surface and extending to some depth. And the snapshot that I've shown here is actually a snapshot from a one-dimensional finite difference model that was implemented in Microsoft Excel using macros. And it shows these nodes. Node 1 is at depth 0. Node 2 is at depth 0.2 meters. This is all in SI units. Node 3 is at 0.4 meters, and so on. And the input data includes the thermal conductivity, the sensible heat capacity, and the latent heat capacity, and a number of other things about the surface. So in this case, the mean annual surface temperature is set to 3 degrees centigrade. So it's presumably a non-permafrost area. The annual amplitude is set to 15 degrees centigrade. So over time, you know, the 3-degree average we would expect to reach. And this model is set up to go down about 10 meters, so almost 30 feet. And it's a pretty interesting model. If I had more time, I would actually bring it up and run it. When you punch this initialize macro, it sets all the initial temperatures to 3 degrees centigrade in this case, since that's the average, and then it'll start to cycle. And you can actually see the temperatures swing back and forth. And the interesting thing about this profile, you see that this is an indication of the importance of latent versus sensible heat. You see that the profile here, the thawing profile, so this, or sorry, the freezing profile, as the material freezes in the wintertime, the temperature profile here is fairly linear, and then there's a sharp break point at the freezing temperature. This is because of the latent heat that's being liberated as the material freezes. So there's more heat being conducted away from this point than there is being conducted toward that point. So the material down here is cooling off, as you can see. Down here it's at, you know, close to 3 degrees. Here it's close to 0 degrees. So there's a temperature gradient here and heat conduction towards in the upward direction, but there's more heat conduction above the freezing point than there is below the freezing point. And the difference is because there's a freezing taking place and latent heat being released at the freeze front here. So these numerical models can capture all the details of the types of freezing and soil cooling that takes place in a real world problem. Perhaps more appropriately for roadway embankment problems would be a 2D modeling effort. I've put, this is a relatively simple example of a finite element grid for a problem that's symmetric. So in this case, we assume that the left and the right-hand sides of the geometry react the same way, so there's no point in modeling both of them. We cut the modeling domain at the center line, and then we extend it out appropriate distance away from the edge of the toe of the roadway embankment and to an appropriate depth. Those can be determined by trial and error or by simply knowledge of the modeler and previous experience. The nice thing about these finite element models is that the elements are flexible. Generally, in order to get adequate numerical resolution, you want smaller elements in areas where things are happening. So you need smaller elements in areas where you expect larger temperature changes. And in the embankment, because of the difference between the asphalt thermal behavior, the side slope thermal behavior, we expect larger temperature changes here. So we have typically smaller elements representing the embankment prism. As you get away from the embankment prism, both in depth and in width, the element size can increase. These models can include detailed thermal properties, boundary conditions, initial conditions. As I said earlier, the commercial codes even include the ability to do a full surface energy balance if you have the data to support it. They generally require a commercial software package. Two that we have looked at recently for DOT, and one that has been used by DOT for a long time is the GeoSlope suite, temp/W. That's been used, I think, both by DOT employees and also by a number of consultants. There's also a soil vision suite that has been available from Bentley. And I know there are some consultants in Anchorage that use soil vision. Both GeoSlope and soil vision are capable of doing 2D or 3-dimensional problems, but again, a 3D model is going to be very, very complicated. And the one last bullet point here that I would really like to emphasize is numerical models can certainly be an exercise in garbage in, garbage out. You have to be very careful about making sure that the model is capturing the important physics of the problem accurately. And one way to do that is to use the model to simulate something that's simpler, but that you know an exact answer for. And this is where something like the Neumann solution can be very useful, because that is an exact mathematical solution to a somewhat real anyway, freezing and thawing problem in soils. And so using a numerical model to simulate the Neumann solution tells you how accurate it really is and whether it's actually capturing the freezing and thawing process properly. So that's something that I would encourage all modelers to do, is that some verification problems before they start running off trying to simulate real roadway embankment problems. And then the other aspect of numerical modeling has to do with numerical resolution. The issue is that as you add more and more elements to these grids, of course, the computer has to do a whole lot more work. It takes a lot longer to get answers. And so there's a desire to speed things up and maybe not use as many elements. But as you do that, you get worse and worse resolution of the temperature changes that are occurring in the problem. And the results drift from reality. And so ensuring that the modeler is using adequate numerical resolution is something that would be important to the designer to make sure you're getting realistic results. And, I would probably, certainly, if I were trying to design something, had a modeler working for me, I would want to quiz them on how they ensured that their model was had enough resolution in it to capture all the important details of the problem that you're trying to get results for. One way to do that is to run the model with a certain grid and then increase the number of elements, increase the resolution, and rerun the model and compare results. That's sometimes called a grid resolution study. And you can do that by adding more physical elements to the spatial domain, and you can also do it in time by running it, let's say, with a 1-day time step, and then running it again with a 1/2-day time step and comparing the results. And if you can, double the number of elements in the grid and cut the time step in half and show, at least for one portion of the problem, that the results are the same, that they're not impacted, then you can be a little bit more comfortable that the modeler is using an adequate amount of numerical resolution to get good results. So last slide, real world modeling challenges. One thing we didn't we talked a little bit about is advection. And this has to do with movement of pore fluids or surface water. Pore fluids could be, again, either pore water or air movement, as in the case of an air convection embankment. In that case, then the convection terms associated with that actually have to be incorporated into that energy balance that I talked about earlier on, and it complicates the modeling. Because if there is important advection going on, not only do you have to solve for the temperature field within the embankment and underlying soil, but you also have to solve for the motion of the fluid. And that is challenging. It can be done by both soil vision and by GeoSlope's temp/W, but it requires additional information about the material properties and the potential that's driving the fluid motion. So that's a real world challenge for sure. A second one is accurate knowledge of the material properties and maybe heterogeneity of the materials. And also the fact that moisture contents may change over the course of the annual cycle. So really accurately characterizing materials is a big real world challenge. And if you're way off on material properties, you'll likely be way off on temperature predictions and freeze thaw predictions. Another one is uncertainty of boundary conditions. without a full met station, sometimes you just don't know exactly what types of temperatures to expect, even air temperatures to expect. And of course, those can have a big impact on thermal behavior. Determination of appropriate initial conditions is another matter. These models, at least a full-blown numerical model, needs to know what the initial temperature is of all the material in the model. So that means that you've got to have a like borehole data with temperature measurements to initialize the model to something that's close to what the real world situation is. For instance, if you have a permafrost layer, you have to know where that is and exactly where it is temperatures are below freezing, for instance. And then the final one I would say is incorporation of climate variability. This is a huge challenge because the climate, of course, is impacting what's going on at the surface, which impacts the temperatures that we're talking about. And figuring out how to incorporate climate variability can be a huge modeling challenge. I mean, one way to do it is to bracket it with relatively warm annual data and relatively cold annual data and see how that impacts the freeze-thaw information that you're getting from the modeling effort. So with that, Billy, finally, I think I'm at an end here, and I'm happy to ask for questions now, or if you'd like, do it later on.
Okay, I have been monitoring the chat, and thus far there are no questions, but a fair amount of dialogue about temp W being the DOT preferred model at this point.
Yeah.
And they, I think Jeff had a few comments. They do try to install weather stations when they can to get data before the project starts, but that doesn't always work for them.
Right.
And for those of you that did not notice up at the beginning that the slideshow is in the chat box, all you have to do is download it for both of them. Please feel free to do that, and we'll make that available to you. We're also recording this so that anyone that wishes to view it at a later date will have that. The folks at Dave Waldo will be putting that up probably sometime in the next week or so. They also have a question, Doug, by Stephen. How do these models match the real world?
Yeah, I would say that it's variable. It really depends on how well you've been able to characterize things. I mean, that and it's hard for me to speak to that. There's probably modelers at DOT like Matt Billings who would be better able to tell you. The one area where I've looked at it a lot, as many of you know, is in ACE embankments, and I have been able to get pretty good correlation, and that's a complicated problem because then you do have pore air moving through the embankment. If I had time, I'd bring up an old paper. There was a paper that I wrote about a pilot experiment that we did with ACE. One of the very first experiments that we ever did with ACE embankments was out at Browns Hill Quarry here near Fairbanks. And that was modeled with, actually was modeled with the grid that I showed as an example in a couple slides ago. And we were able to, with the model, predict the shape of sort of thermal circulation plumes in the embankment. And we had enough data from the project that we were able to actually see those same plumes within the data itself. And especially with a convection problem, you need a lot of data. So in that case, we had an array of temperature sensors on, if I remember correctly, I think 2 foot by 2 foot centers throughout the embankment prism. So there were a lot of temperature sensors. And so we have been able to pretty accurately match experimental and real world measurements with numerical models. It's hard to say in general how the comparison goes because most of the time, we don't have the real world data after the fact to compare.
Okay. I think I've answered Amy's question. Amy was asking about whether the manual covered utilities, and it does not. But I would say that many of the principles that that are in the manual or in the synthesis do apply to utilities, and it does certainly the comments on thermal modeling do apply as well.
Right, right. Yeah, I mean, the comments on thermal modeling are very appropriate. If you have buried utilities, for instance, the same kinds of things apply as for a roadway. For instance, if you have a buried pipeline, you probably have symmetry, horizontal symmetry about the center line of the pipeline. You could build a thermal model. Primarily, it would be a function of heat conduction in the soil surrounding the pipeline and so on. So many of the things that are in this chapter on thermal modeling apply equally to utilities or roadways or other linear structures as well.
Okay. Well, we need to move on in order
Yep.
to finish up on time here. So I'm going to share my screen, Doug.
Okay. Well, let me just say that I, as Billy said at the beginning, I'm here in Fairbanks. I am retired. I'm happy to connect with any of you who have questions about Chapter 4, or if you have questions about thermal modeling. Yeah, please reach out and feel free. Thanks.
Okay, thank you, Doug. And as I say, as Doug says, he's certainly available to you if you need, and he does occasionally do projects for DOT. I think he's got one going now on ACE. Uh-oh.
You clicked off for a second, Billy, but I can hear you now.
How about now?
Yeah, you're kind of
I got to restart. Okay. Am I back? Doug, can you hear me?
Yeah, you're back.
Okay. Some reason or another, my Zoom decided to quit me. Okay. Well, as we'll continue on, and we're going to talk a bit about Chapter 5 now. I want to do what I wanted to do. Let's reshare here. Okay. Hopefully everything is going okay now. Doug, are we on the second slide? Just make sure.
Yep.
We're building. Okay.
Yep.
Doug just talked about this just a few moments ago, but I think it's really important that we reinforce the concept of the energy balance. And so anytime you're building on permafrost, a designer must understand the energy balance and the impact of the construction on that energy balance. And as some of the work that I've been doing in Point Lay, which is their infrastructure is failing rapidly. Wainwright is also having some problems. And it's really because we didn't pay enough attention to the energy balance of that. So it's critical that we pay attention to that and we understand what we're doing to that energy balance and the consequences of setting that energy balance. So you'll see this theme coming up over and over and over throughout the synthesis. So chapter 5 is really talking about design alternatives. I'm not going to go into great detail in all of these, but I'm just going to give you a sense of some of the options that you have available to you, perhaps when you might want to think about using those techniques, and when you may possibly even want to avoid those. So there really are only a few options that are available to you. One is to avoid the permafrost altogether, which is probably the best one. You can also manage the permafrost thawing in several different ways, or you can try to preserve the permafrost. So we'll be talking about each of these in just a little bit more detail as we go along. Which one should you choose of those three? Well, the policy of the Alaska DOT and as going back to the 1800s, actually, it has been to avoid permafrost whenever practical. Um, Fully recognize that there are competing requirements such as grade, site distances, and all of those kinds of things. But if, when you can, try to avoid it. Um, Managing the thaws, attractive and warm permafrost, such as around the Fairbanks area and south, pretty much anything south of the Yukon River on our primary network. That is a good choice, and where the mean annual surface temperature is above freezing. And Doug talked a little bit about the surface temperature and how you might get to that. But it's important to recognize that if you're in those conditions, and especially when you start adding the increases in temperatures that we're seeing in our climate these days, it's when you're at or near that point, you probably want to really start thinking about managing your thaw. And then preservation of permafrost, anytime you're in the cold permafrost or when the mean annual surface temperature is below freezing, that may be a point in time when you can consider trying to preserve the permafrost. Um, Again, we'll see in chapter 10 that the climate is changing, but hopefully in that chapter, you'll start getting a sense of what tools are available to you in order to take that into account. Uh, the avoiding the permafrost is not a new concept. When the Richardson Highway was realigned during 1910, William Richardson, Captain Richardson, was in charge of that. Um, that was a primary consideration. Wherever they could, they went out of their way to try to avoid permafrost, recognizing that if they didn't, that it was going to be problematic for some time to come. In the 1950s, when the Alaska Road Commission was established, uh, they also have put it in their policy that it would be that they would avoid permafrost whenever practical. It was in written policy, and for all practical purposes, I guess we could say that that's still very much in effect. One of the things that I'm seeing occurring more and more is the desire to upgrade our roads and airports and try to, in many cases, uh, looking at relocating those. I just be careful when you do so that you do it with forethought, and especially if you're moving off of low ice content, no permafrost into permafrost, you may want to carefully think about that and the impacts it may. In general, if you're building on stable permafrost, and there's a little bit of discussion about that in chapter 2, um, that's probably going to be okay, but make sure that you really know what you're getting into as a part of that. And interestingly enough, those of you who have taken the pavement design course from us a few weeks ago, or actually some of you probably a year ago, um, there is a life cycle costing software in there that can help you through that maze of, is it really cost effective to move routes on or off the permafrost as far as that goes. But that tool is available to you. It's fairly easy to use, and certainly could give you some insights into the cost of moving the roadway. Um, we can also accept the consequences of thaws. And first, there's no way that we can totally avoid permafrost, especially as we move north where we get into continuous permafrost. So we need to be able to understand the consequences of moving on to permafrost and be able to address those issues. Um, it's not always practical to conserve preservation features, but such as subcuts or pre-thawing. When I say subcuts, we're trying to remove the permafrost entirely and go that route, or pre-thawing may not be practical. So if you're rerouting, carefully evaluate the in situ soils and know what you're getting into as you move forward. Techniques to minimize the impacts. Just because um, uh, you can't keep the permafrost thawed, there are some things that you can do to minimize those impact. And those include minimizing disturbance of vegetation. We'll go into that in a little more detail. Um, Hand clearing for site distances, and we'll talk about that a little bit, the impacts of that. Uh, we always want to minimize the disturbance of drainage patterns because of the advections that Doug was talking about a little bit earlier. And we'll talk about that a bit more detail. And when possible, we just absolutely want to minimize the disturbance of the existing embankment, especially if it's frozen, because you could disturb the balances that has been established over many decades in there. And so, if you can, don't dig into the embankment any more than you need to, especially if it's frozen. Another option for us is to use geosynthetics in there. The two popular means of using geosynthetics, one is what we call, people often call a pillow wrap, which is depicted here in the lower right-hand column. The upper one is the implementation of that, where we lay it out and wrap it over. The idea is to maintain the core of the embankment in good stead, and we'll let the side slopes go as they will. The other way to do it is just simply what we call, sometimes called the phone book method, where you just lay the fabric out straight and you don't wrap it over the top. And you usually take that out a bit further so that you can get tension. In both cases, you're depending on the tension of the insulation being developed, so you want to put it in tight, and you want typically to use a fairly high modulus material or a fairly strong material in that application. So geosynthetics do work very well as a separator to keep the fines from coming into the coarse grain materials on your embankment. We use, I know that DOT uses a tremendous amount of fabric for that purpose. It also minimizes the longitudinal cracking and the lateral spreading in there, but it's essentially been shown that it is ineffective reducing the vertical displacement. So if you're using it in there trying to reduce the vertical displacement, it's probably not going to be too effective for you, but it will help you out in the lateral spreading area. So be careful as to the application of it. We have had a few applications where it did not work very well. I was called out to Kivalina one time where they're building a new runway, and they were having the geosynthetic. Whenever a piece of heavy equipment went across it, it would blow up like a balloon and pop, and a wet, gooey mess kind of flew out of that. And as a result of that, we found that the geosynthetic was holding the water down and basically ended up ripping the fabric out and letting it drain and then completing the runway. It's performing well now, but geosynthetics can do harm. Pre-thawing has been used in a few cases for those in the Fairbanks area. Some of the roads to the south of town have used pre-thawing on a few occasions, and it works well. And where you've got warm permafrost and warm areas, such as Fairbanks, and where the permafrost is relatively thin. In that case, in the cases around here, we sometimes only have a few feet of permafrost, and to pre-thaw that works out pretty well. But you do have to plan 2 or more years in advance to make that happen. And so it's really a good idea before you decide you want to go that way to estimate the thaw rates carefully. And if you do proceed that way, you might want to put some thermistors in so that you can measure that progress. But it is an effective way. And in the Anchorage area, it might be effective for you as well. There are shoulder modifications that you can do if you're going to allow it to thaw. Stabilization or toe berms. I spent a lot of time trying to figure out why the Canadians were having good luck with it, and the Alaskans were not having very good luck with it. And after I took a few trips with the Permafrost Working Group that's supported by Transport Canada, I realized that the Canadians tend to use it more in the cold permafrost areas, whereas uh, we in Alaska have tended to use it in more of the warm permafrost areas. And so what I realized is that it works well in where you've got cold permafrost, such as north of the Yukon River, and poorly where we have warm permafrost. This photo, if you'll notice that there's a lot of water and a big thermokarst at the bottom of that. This is a section at Alder Creek, just south of Fairbanks. Where that, if you look over to the left, you'll see a pipe sticking out of it. That was an old air convection culvert. That used to be about 10 to 12 feet above the surface of the surrounding terrain. And over time, because uh, the snow that was thrown out there due to clearing of the roads took the mean annual surface temperature. We measured mean annual surface temperature on those tow berms to be about 40 degrees or more. And so we found out that that just wasn't going to work for us, and it thawed. And so we finally gave up and used the pillow wrap on there, and that's actually performing a lot better for that. So be careful when you use the tow berms and make sure that you understand what the mean annual surface temperature of the top of that tow berm is, and that you can estimate the thaw consolidation of that. Another approach to that is the barn roof shoulders, where you go out to the edge of uh, shoulder, and then you build the remainder of the shoulders, something on a 10 or 12 to 1 out for a little ways, and then you come down with your normal embankment side slopes. Um, and if maintenance clears those, we found that those worked out very well. It kept the longitudinal cracking outside of the traveled way, and most of that occurred in the barn roof section. The problem is that M&O just simply doesn't have the funds to clear those, so they stopped clearing them, and as a result of that, the effectiveness of those barn roofs was diminished dramatically. So whenever you choose an approach, it's really good to speak to the folks over at M&O and make sure that they are willing to do what it takes to maintain those. There are a number of ways that we can preserve permafrost. I've listed these in kind of a generic type of listing. Insulation, which is probably the most common of those. The second most common is probably air convection. Most of you know about air convection or ACE, air convection embankments, but there are a couple of other techniques that are being used. Shading it works out really well, because if you look at the solar input, that can be degraded or eliminated or reduced. Thermal siphons are occasionally used. And of course, there's some things we can do to try to use winter construction to help preserve that permafrost. So insulation, there are really two types of insulation. Each of them have their pluses and minuses. Extruded insulation, those are the ones that are produced by Dow Chemical and Owens Corning. There was a third for a while. Dow is usually what we call the blue board. The pink board is Owens Corning, and there was someone making a yellow extruded for a while. I haven't seen that in a long time, but if you run across that, you can usually tell what that is. The advantages of the extruded, it absorbs less water than the expanded, and it's also less sensitive to the water content just because of the way that the air voids are produced in there. Over the long run, it typically has a bit higher R value, but it is more expensive. So you kind of have to trade that off. The expanded, it's less costly. That's one of the advantages. Another advantage is it's made in Alaska, so you don't have the large shipping costs to get that up from the lower 48. but it does absorb more water over time. And there are several reports out on that confirm that. And if you really want to know about those, I put out a report a couple of years ago. Dave Esch put one out in the 1980s, and the folks over in Ottawa, Canada, put one out about 10 years ago. So they all have very similar results of that to that, but they do vary a little bit in the details, but all in the same trend. So about 25% lower R value over time. So most people right now are using the published R values of these products as they exist on the shelf. But I would encourage folks to start thinking about using the in-service R values um, instead. That will give you probably a better indicator of how well these insulated materials are going to work. And either Doug and I can talk to you in more detail about that if you would like to know more. So where do we put the insulation? Well, I've talked about that, and Doug and I had many discussions on that. And what we basically came up with is just that you won't put hot and cold foods in your cooler. You really shouldn't put both hot and cold soils beneath the insulation. Think of that insulation as kind of a big cooler. So, I wouldn't put my hot lunch in with my cold drinks and the ice in that cooler. I'm either going to put hot stuff in one cooler and cold stuff in another. So one of the things you want to look at is when you're going to be doing your construction, and you really need to carefully consider uh, when you're going to put it down, do your construction, and why you're going to do so. So if you're going to be doing it in the summer, you probably want to put the uh, the insulation closer to your permafrost. Um, hmm, I mistyped that. But you want to put the insulation down near the permafrost, but you don't want to leave the permafrost exposed more than a few hours. You want to get down to it, put your insulation down, and start getting it covered as quickly as you can. Even better, in order to avoid the problems that you're going to have with potentially thawing the permafrost, is to do it in late spring or early fall, or late fall, or early spring and late fall, sometime in the spring and the fall, in order um, to get that, to minimize the warming of that permafrost. So um, you really want to minimize that. The other part of it is if you're going to do it in the winter, now you can place it much higher because you've got the embankment frozen, and so the other approach there is to dig down to the permafrost, put the soil down, let it freeze, and work your way up, and then uh, allow all of that to freeze before you put the insulation on. But the thing that you really want to concentrate on is that last bullet down at the bottom, the yellow one, says you want to minimize the exposure of the permafrost to heat. That is really what you're really looking for in order to try to maintain the permafrost beneath your insulation. Um, Use of air convections. They're really, right now, there are really three types of convection that people are using. The air convection embankments. I'm just going to hit the highlight. If you really want to know the details, get a hold of Doug. In fact, if you want to know the details of any of these, Doug is very adept at running the models for you and helping you understand those. I just understand them from more of a conceptual viewpoint, and I can give you some information about how well they work. Air convection embankments, which most of you are familiar with. The air convection culverts, which is shown at the bottom, and I'll go into more detail on those. And at the top, there's something that was developed by Guy DeRay over in Canada, which he calls a heat drain. They all work in a very similar manner. They're using air convection to cool the embankment. Air convection embankment, as you see in the bottom right there, basically what's happening is the ground is heating the air in the coarse rock that the embankment is made of. That causes convection cells to be produced, and that heat is released to the surface of the roadway. and as a result, you're getting good cooling. Even in the warm areas around Fairbanks, the air convection embankment that Doug is monitoring up on the university campus on Thompson Drive, we're still getting cooling after all these years, even though we've had a few warm years recently. So that's working well. There's another way to do it. That's called the ventilated shoulder, which is in the top right. Basically, it's using the same pile of rocks, but we don't put it on the interior of the embankment. And we're using that to cool the slopes of the roadway. One of the issues there is there's a tendency for air to blow through there, wind to blow through there and cause some issues.
Billy, I'd just add one quick comment here too. In your note there, it indicates a 5-foot minimum, but we've been doing experiments on that, and I would say that the jury is out in terms of how thick those ventilated shoulder layers need to be. Maybe as little as a few feet might work in some cases. So the jury's still out on that one.
Okay, thanks, Doug. That comes from a little bit of an older publication. But as I say, these things have proven to be most effective in, of all the techniques that we have, but it's probably the most effective in preserving permafrost. But it is expensive where you don't have rock, because getting rock can be very expensive for us. And ventilated shoulders, as I said, may be affected by wind. I like the ventilated shoulders because it can be used as a retrofit, although I've only seen that done maybe in a couple of applications. Air convection culverts. We have used those a couple times within the state, and the Canadians are using them on a few occasions. They really kind of work very much the same way as the ventilated shoulders. If you look at the graphic on the lower right, at the bottom, the air comes into the culvert, and it is warmed by the air and then exhausted by the chimney. And so if you look at the upper right-hand picture, the far culvert is the entrance, and that nearer culvert at the top is the exit, and then the near culvert at the bottom starts the next cycle. Works very well for cooling the shoulders. It does nothing for you in the center, but it does cool the shoulders very well. Relatively inexpensive. The first ones we used metal pipe, but most of the applications that are being produced now are using the plastic pipe, so it's much easier to put in, much less expensive. One of the keys is to put it high enough that you're not going to get water in the bottoms of it. That was the first couple we did. We made that mistake. We didn't get it high enough in the embankment. So it's really neat to get that. They will cool about 4 feet and 4 feet around the pipe itself. So that gives you some idea of the area of influence. The other thing is you'll notice that there's a cover on the front, on the lower ones, to keep air coming in and during the summer months, especially in windy areas. Heat drains, again, is very much the same concept, except we're using geosynthetics with an air gap between them, which are commercially available. They're often used as vertical drains. If you were to go looking for them, look for vertical drains. And so again, you can see the pipe with the blue arrows down there. It goes in there, and then the ground heats the air. Due to convection, it goes up and is exhausted in the other pipe. The right-hand picture is a photo that I took in Silhouette up in Nunavut, in the Canadian provinces, and that one's worked pretty well. There were a couple of others put, one at Beaver Creek. One of the issues it had there, again, didn't get it up high enough to get it out of the water, and so it ended up plugging up. So same kinds of issues with all 3 of these. Make sure that you account for the water in there. Okay. Another concept, this was developed by Dave Esch way back in the 1980s, is shading. And this is at Beaver Creek, a Canadian experimental area. If you ever get the chance to go down there and look at that, I'd encourage you to do so. It's got many of these features there all side by side so that you can look at them and understand how well they're performing. But it's really simple in concept. All we're doing is we're putting shade over the shoulders, and that causes it to cool. But the neat thing about them is in the wintertime, because that's the snow is being held up off of the surface, air is able to flow underneath these sheds, snow sheds, and cool the ground there. So they really work pretty well in both summer and winter. And we've seen side slope in Beaver Creek. They measured the mean annual surface temperature has been reduced from 39 degrees F down to 28 degrees F. So that's a substantial cooling as part of that, and certainly reduces the amount of thaw settlement that you're getting in your shoulders, which often show up as longitudinal cracks in the travel way. One of the, we had discussions a few times about this with the folks in the DOT traffic sections, and they're concerned about these things being within the clear zone, so they typically require guardrail in those areas. So in the Canadians, they did not. So it's just something to be aware of. Okay. Thermosiphons, developed by Irv Long way back in 1956, first used in 1960s that year. I was just the other day trying to figure out how to explain to a group of high school kids in Point Lake how thermosiphons work. And I came across the water cycle and I realized that it's exactly the same process in the water or rain cycle that is occurring in the thermosiphons. The sun heats the water, which then turns to vapor. It goes up, and as it goes up, the air gets cooler, and as a result of that, it condensates, falls back down to the surface as rain. And so basically, if you look at the graphic in the lower right, exactly the same thing is happening there, except we're using the ground heat to heat the permafrost, or heat the fluid in the thermosiphon. That heats it up, and then when the air temperature is low enough, that that heat is rejected through the condenser fins, and then that causes the gases to go back to liquid and fall back down. The only real difference between these two systems is the fluid and the pressure inside the vessel is a bit lower, and so there's really not much difference in that. They only work in the winter, so that works out really well for us. They're effective, but they're quite expensive. And there are, John Zarling has a publication out on that, and there are several others describing the effectiveness of thermosiphons. And you really, I point you to that if you really want to know more about those. There are several types of thermosiphons out there. They all work in exactly the same way, but the configuration of them is slightly different. The vertical one is the ones that we're most familiar with. They're the ones that are used primarily around buildings. They're not too effective for us in roadways, but they just basically a vertical pipe stuck in the ground, and then we have radiators on the top in order to cool them, and they, as I say, work very well for buildings. The flat evaporator, that one basically can be going beneath the road, but the evaporator is turned 90 degrees, anywhere from 90 degrees, maybe up to around 60 degrees. They're bent over. And as I say, they work very well. One of the reasons that that's done is to reduce the issues of getting in the way of sight distance. Flat evaporators, the flat loop, basically you put a loop of pipe in the ground and then connect that to an evaporator, and the fluid really goes in a loop. And that's all described in more detail in in the synthesis. And then the buried condenser, somewhere the hairpin thermosiphons, which we have on Thompson Drive. The whole thermosiphon is contained within the roadway. And I know that all but 2 of them are working because I went out and looked at the roadway last winter, and right over those thermosiphons, you can see that there's no frost on the roadway. And so it's very clear whether they're working or not. But you really have to make sure that you maintain these and make sure that they're working, and recharge them as necessary. Again, much more detail on these types and the description of these are contained within the thermosiphon, or within the synthesis. We're seeing more and more winter construction as we go along in an effort to reduce the impact of thawing on the permafrost during the construction phase. So a couple of different approaches to this. One is to allow the subgrade to freeze and then apply frozen material. The downside of that, while it's probably one of the less expensive ways of doing winter construction, is poor compaction. Frozen material just simply does not compact very well. If you're going to do that, try to use low moisture content soil because you'll get better compaction out of that. And in the lower embankments where it's best used in the lower elevations where thawing is unlikely, and the amount of it's not up in the structural section. I would not ever use this in the structural section of our embankment. If you place it in thawed condition, allow it to freeze before the next lift, that works out very well. It is effective, but it is a bit more expensive because the contractor has to haul that material, get it in place, compacted before it freezes. So he's got to really have everything going in his way in order to make that work. And in some cases, for example, if you're in Barrow or in the northern part of the state, that thaw material is going to be essentially impossible to come by. And so that's probably not going to work very well for you. And then finally, place it for frozen material in the lower levels. And then the next summer, continue with conventional construction. That protects the permafrost and also reduces some of the cost. So in summary of chapter 5, first approach is to avoid permafrost. You want to choose your approach, and that is this decision needs to be made very carefully because you may be trying to do something that is impossible to do. So pick one of these 4 and base the rest of your design on that, and make sure that you're consistent in what you're doing. There are all of these things that I've presented in chapter 5 use current technologies, but they only address localized problems. You're not going to be able to use these technologies for miles and miles and miles of roadway. So in that case, you're going to have to work with dealing with the practicality of thawing permafrost. So it's just the nature of the beast. No technique fits all situations. You've got to carefully think about which one fits where you are. And frankly, they're all expensive. So, you really need to choose which approach you're going to go after very carefully. So with that, I'll open it up to a few minutes of questions. If anyone has got that, let's see if I can stop sharing my screen for a moment and scan through. Okay, I'll try to, before we leave here, I'll try to resend these, the slide deck. And
Really, while you're sorting through the chat, I might make a comment too, and I've just thought about this on the surface at a very preliminary level, but I have a feeling that more and more given what we're seeing with temperatures, et cetera, that pre-thawing is probably going to be a more important approach in the future, but developing good methodology for doing, pre-thawing quickly and effectively, and then dewatering and generating a stable thawed base. There's probably a lot of work to be done to figure all that out, but it seems like, we almost have to head there in the future.
Yeah. There were several comments about winter construction, and I didn't go into very much detail on that, but the timing is very critical on that. I typically don't necessarily recommend doing that construction during the coldest parts of the year. I would try to do it in the late fall and perhaps early spring, and in most cases, in order to make it easier. If it's 40 below out, I certainly wouldn't be doing it, but kind of in those shoulder areas is much better way to do it. And someone said something about the use of geosynthetics, and I do agree that you need to be very careful when you use it, how you use it, and make sure it's going to be done for that. Some of the folks are talking a little bit about Transport Canada is looking at pre-thaw as well. And yeah, I did use 1 point white paint and white marble for chip seals, and it did reduce the temperature of it, but over time it became dirty and became less effective as going along. The Corps of Engineers at Greenland have stopped painting white because what they found was that it worked very well in the beginning, but after 6 months, the impact was much less because of the discoloration of that surface.
Yeah, I can tell you as a high school student growing up in Fairbanks, when you guys painted part of Farmers Loop Road white, that was like the perfect place to check out our big block cars.
leave it to a mechanical engineer. Okay, so let me go back and share my screen. Hopefully it will work better this time. What happened? Okay, can we see that okay? What's going on?
Not yet.
Okay. Let me try something else. Okay, can you see this okay?
Yeah, that's coming through.
Okay. Okay, let's talk about drainage a little bit. And one thing that I've learned through my many years of dealing with permafrost, the fastest way to damage permafrost terrain is to change the drainage patterns, no matter how small a change. The photo that is on the screen right now was a fiber optic cable that was placed, and they placed it only about a foot down and disturbed as little of the terrain as they possibly could. And 4 or 5 years later, this is what it looks like. Very, very minor. I mean, nobody would have thought it would have done anything, but it is eroding very rapidly, both through the flow of water advection, as Doug talked about earlier, and due to the mechanical erosion that's going on as it thaws. This is ice-rich permafrost. you melt the water, and you've got a problem. So one of the things that I always uh, try to teach people is make sure that you account for the water. Um, Here's a graphic showing what the water, what the profile of permafrost may be. We have the active layer, and right on the bottom of that active layer, there's often what many call a perched water table, groundwater. Um, that is the water that can't penetrate the permafrost. And then we have the permafrost itself, and then below that we may have a sub-permafrost groundwater. One of the things that happens if you drill a well into that sub-permafrost groundwater, um, that's often under pressure, and you end up with an artesian well coming through the permafrost, which then very rapidly melts the permafrost, which allows the water to come through even faster. And once that gets started, it's very, very difficult to stop. There's a couple of instances on Farmers Loop where that happened, and the cost of stopping that was tremendously high. So be careful about drilling into that.
There was
Under
an incident about 10 years ago now out in Goldstream Valley, which required 20,000 gallons of liquid nitrogen to solve.
Yeah, so it's quite difficult to stop. Um, Interestingly enough, this has been understood for quite some time. The Alaska Road Commission in the 1950s noted that the drainage in permafrost requires careful inspection of the terrain, including water movement in the active layer. Um, so it's been known for a long time, and it's been discussed a long time. But unfortunately, even today, many of our designers tend to uh, ignore that perched groundwater and not account for it. It can manifest itself in a number of ways. Just simply building a road across the tundra can impact the drainage in that active layer. And this is a series of this is a transect that was taken at Lake Colleen up at Prudhoe Bay, and the roadway was placed in 1972, and I think the last one goes through about 2012 or so, 2013. You can see the change. The water is flowing from bottom to top, and you can see as time goes along that many of these, what were fairly stable looking ground, the,
Hey,
the ice wedges are being melted because of the standing water,
no,
and as a
apparently
result of that,
there's
it's causing
another
problems.
module that they're going over that was not on the schedule. So I'm like,
Someone's
yeah,
not.
it was supposed to be from 10:30 to 12.
Okay, so you really want to pay attention to keeping that water moving, especially if was something upstream that could cause a problem. But that does impact the roadway as well, because all that water is now imponded against the roadway. We've talked about this situation where we're getting water ponding and thermocosting along the TOA slopes. We've all seen that over the years. There's lots of examples of that along our roadways. And as those continue to grow, they end up causing longitudinal cracking in the travel way, and maintenance has to deal with those. So if you can figure out a way to get that water away from there, it's much better to do that. It also affects our pipes, our culverts. In this case, there was a thermocross that started forming upstream in the inlet section of that because of water flowing through there. And as a result of that, some of the pipe was lost, and the road was actually moved a little bit to the left in order to avoid that thermokarst. There are some things that you can do. One, this was a fairly innovative way of doing it. I saw it used for a while. It's not being used as much now, but simply releasing the water a bit away from the roadway by extending the pipe. One of the things that you need to be very careful of is that first section, which is usually about 20 foot, you need to embed it in the embankment well so that it doesn't get damaged. So it certainly works well And as I say, you can see there that the water being released. That only works well when you have water flowing either just in the spring or you're trying to release water coming in from that perched water table. It does not work well in streams. So don't try this in streams because you can end up with a buoyant failure as a result of that. Another way that has worked successfully where you have rock is to put some rock there. If you put enough rock, you could end up with a ventilated shoulder, but in this case they didn't. But just putting that rock there helps reduce the amount of thaw that is going there, and certainly helps stabilize that situation and reduces the mechanical erosion that's going on there. So um, that works out pretty well for you. Uh, there have been a number of people suggesting putting insulation in the culvert. And one of the things that as I monitor that, there have been a few installations where that's been put in, but it's not being used very often. But if an established channel and a talc already exists under that channel, the insulation is not going to be any value to you. So if you've got something like the graphic shown there on the right, and you're trying to put a culvert through the roadway to address that, I would not consider insulation because you've already got a talc under there. Putting the insulation, the water is going to continue flowing underneath the insulation, and you could possibly create a worse problem by putting the insulation in there. But if the water is only going to flow a short period of time in the spring, or the flow is just occasional, then you might get something out of that because the talc hasn't been produced underneath that particular area, and you just got basically that perched water table. If the water exists in that active layer, insulation may be of value there as well. So be very careful of that. Um, some of the thermal models may be able to help you there, but be very careful how you put those together and which model that you choose, and make sure that you check them out, making sure they give you reasonable answers in that. Some other thoughts on drainage. Uh, One is that use a slightly larger, at least one size larger culvert to account for thaw settlement that allow your pipe to last a bit longer. I generally suggest using a bit heavier gauge culvert. By the way, I think Northern Region now, my understanding is that the 36 inch is the minimum size culvert that they prefer to use on the continuous permafrost areas. If you're using a spiral culvert, which is very popular here in Alaska, well, that J seam for strength. I went and looked at all the J seams along the Richardson Highway a number of years ago, and every single one of those J seams that were on permafrost had failed. And so we require now that they be welded, and that seems to have fixed that problem. If you may want to consider for the larger colors using a multi-plate instead of a welded J-seam. That seems to do that. And the last thing I'll leave you with on the drainage issue is alter the channel alignment only as a last resort. And the reason for that is the existing alignment of those streams has a talc beneath it. And if you realign that, then it's got to reform that talc, and you're probably going to get a lot of thaw consolidation as part of that. I'll answer the questions on this at the end so that we can get through the other two sections before that. So let's talk a little bit about construction and maintenance. And if you remember nothing else about these two chapters, is small mistakes, big consequences, and consequences that cannot be undone. Again, this is a similar photo that I showed you earlier. The chances of undoing the damage done by that little thin fiber optic cable, it's just not going to happen. It's going to be there for pretty much forever. Even if it does get vegetation back going, that drainage channel is going to be there. So really be careful about anything that you're going to do, especially anything outside of the roadway prism. Minimize disturbance. Simply clearing the trees, and this was done by Lindell way back in 1973, where he went out to the Corel permafrost site on Farmers Loop, and simply clearing the trees, he found that it increased the thaw consolidation by almost 6 feet over 5 years. And that's over the undisturbed areas. And clearing the vegetation in its entirety would result in 22 feet of thaw. And so you can see that the more you disturb that permafrost, the greater the results, and the likelihood of repairing that become almost nil. It's really important that you pay attention to permits, and I should actually say beyond that, the design of the rotary prism, because as I say, small mistakes can add up very quickly. So I suggest that everyone, including equipment operators, know about the provisions of the permits and the regulations that affect their work, and make sure that they adhere to those at all times. Discuss the permits and regulations before beginning any work. So if you're going to start something new, take the time to sit down with the contractor, the state personnel, as well as the equipment operators, to make sure that everyone understands what those permits and regulations say. Managing unforeseen ice. It happens all the time, especially here in the northern region. We run into ice that was totally unexpected, or it is more of it than we anticipated. So in general, you probably want to stop the work and contract the materials engineer to look at that and get that looked at quickly before you continue on. Specification 108, 106 for the state folks is what controls that. And then work with the materials engineer and the contractor, and you definitely want the contractor involved in the discussion, because they're going to have to affect any changes that you make. First thing you want to do is stabilize the situation. You don't want to let that permafrost continue thawing. I've seen some results of that. In one case, we made a cut. DOT made a cut in the roadway. All of that material melted, thawed, ran down the hill, and then completely inundated the landowner at the bottom of the hill with gravel. And a lawsuit ensued, and state spent a lot of money paying for that. In the end, it actually improved the quality of the land he had, but he got the money anyway. Identify the extent of the ice. Certainly it's something that you want to do. There are a number of techniques which we talked about in chapter 3 that can help you do that. And then develop a plan of action. And that's probably going to require a change order in that, and then execute that plan. So it's really important to get the subject matter experts involved in the solution very quickly, and make sure that you don't delay in doing that. Don't really think about it. Just get on the phone and make the phone call. Okay. We also, for the M&O folks, especially, we want to monitor the drainage patterns. If you start seeing the drainage pattern causing an issue, get with the regional hydrologist, and I probably would say the materials engineer as well, to look for changes in that. It may require some backfilling. It may require additional culverts, whatever that may be. Thermokarst ponds need to be corrected or filled in order to do that. And the other thing is, for the M&O folks, make sure that all your culverts are working correctly. I suggest every 2 or 3 years, taking a good close look at them, clean or make repairs as necessary in order to ensure that they're working properly. So the last thing we want to do is impound water uphill of those culverts and creating larger thermokarsts. When we fill longitudinal cracks and thermokarsts, I would suggest avoiding using pea gravel or sand. It's easy, it pours in there very nicely, but the problem with that is it still allows water to continue on. I know some of the folks that I talked to up on on the Dalton were doing that. They were putting pea gravel in there because it was easy, and water would flow in there and continue to melt the ice wedge. What you really want to do is stop the water from flowing down into the permafrost. So you probably want to use something more like silt, to fine grain material to get in there to reduce the adduction of water. Um, People have used a, a slurry, but you want to keep the water to a minimum in order to, you don't want to add a lot of hot water to it as part of that. But a little bit to help to get the water, get the silt in there is probably okay. Winter construction, we've talked about that a bit in chapter 5. But the important thing here is for the construction people is to know the plans and specification, know exactly what is required in that. And if there's any questions as to, and you don't understand why that it's being done the way that the way the designer wants it done, feel free to contact the designer and have that discussion. In some cases, the designer might immediately push you towards the materials folks to answer that, but make sure that you know what those are. And it's probably better if you know a little bit about why you're doing what you're doing. The cost of winter construction is high. It's due to increased time requirements and the problem issues with maintaining equipment in those temperatures. So that's part and parcel, but I'm assuming that the designer has taken that into account in the decision process. And so if you have any, again, concerns with that, talk to designer in that and make sure that you do it. But again, I would not necessarily try to force a contractor to do it in the deep of the coldest bowels of the winter. Um, know that your contractors are likely to complain, but they bid on it and the specifications are what they are. But listen to the contractor. They may have a way to accomplish what you want in another way. There have been a few instances where that did occur, but just recognize that that's going to happen to you.
And Billy,
For the
just a
M&O
quick,
folks,
I just got a quick comment on winter construction. I think generally you're better off if you can start early in the spring and complete things, because you have a better chance of trapping the winter's cold, obviously, on the ground than you do if you do it in the fall. So I would put a vote in for spring construction, early spring construction, whenever it's possible.
yeah. In some cases, it becomes difficult to get material, so you got to take that into account as well. When you're leveling roadways, the current practice is in general to mill or break up the pavement before beginning, and the reason for that is it reduces the amount of material that's going to have to be brought in, because you can once it's milled or broken up, you can level it and create a new grade. Level and compact material to make it smooth. Um, there's really no need to bring it back up to original grade unless there's site distance issues that you need to deal with as part of that. But if you're in doubt, check with the traffic section and they can help you through that process. Um, and then if the route is paved, you can use a number of different materials, high float, chip seals, or hot mix. And that's going to depend on where you are and what is the most cost-effective means of doing it. Um, if it's something that's going to occur on an annual or even a biennial rotation, you probably don't want to put a very expensive surface on there because it's not going to last very long for you. So in summary, we want to minimize the disturbance. As I said, just simply clearing the trees can cause 15 foot of thaw over 5 years. And that's really because the shading is now gone. So pay attention to that. Be careful with the drainage. As I say, the fastest way to thaw permafrost is to put water on it. And if you've got problems, ask for input from the materials folks or the design group, and that should help you out a little bit. And finally, as I said at the beginning of all of this, small mistakes can result in big consequences. So with that, I'll stop sharing my screen and be happy to answer any questions. Yes, Henry Cole said that make sure that the thaw pipes are function correctly, they're essential. I fully agree with that. Um, a bentonite slurry can do it. I have used bentonite for that purpose on a few occasions. It's easy to ship, but sometimes it's pretty expensive. So um, that's one way to do it, Jeff. Um, I have used just regular silt as well, and had good success for that. Um, uh, Yeah, Heather's indicating that tooth-all pipes may be better for pipes over 4 feet. The key to tooth-all pipes is getting the water thawing, and once you get the water thawing, it will do the rest for you. But whether you use one or two, a lot of people use two just so they have a backup for that. And then Jeff was saying um, excavating ice-rich permafrost is much easier when it's cold to stay frozen. I fully agree with that for more than one reason. One, it's easier, but the second reason is if you do it in the cold, you're also not heating it up and thawing it and letting that get away from you. So let's see, did I miss anything? Oh, Jeff was asking, do culverts typically have a net cooling or warming effect? Dave Ash actually did a study on that in the early 1980s. And when I was working for him, we'd go out and measure the temperatures under culverts. And we did find that culverts that are 36 inches and larger, assuming that there's no water flowing through it, or net cooling. Anything less than 30 inches is net warming. And I think probably that the reason for that is that the smaller culverts end up getting plugged with snow and don't allow air to flow through that. So yes, you can get net cooling out of culverts. And yeah, I will agree with that. Culvert modeling from a thermal standpoint is very difficult to do. Um, okay. With that, we've got a couple of more minutes. If someone wishes to unmute themselves and ask a question at this point, Doug and I'll be more than happy to answer your questions. And if you disagree with something we said, that we'll discuss that too. Well, I'm going to assume that silence means that we've answered all your questions and that you're happy with what we have. I will note that the final webinar will be hopefully in about 2 weeks. I need to check with the other two authors, and that will be going over the slope stability chapter. I think that's chapter 7, and chapter 10, which is dealing with the climate changes and all of that. So with that, I'll let all of you go. As I said, this has been recorded, and we will be happy to share that with you. I'll give that to Dave Waldo, and he'll share it with you here probably within the week.
Thanks to everyone. It was an interesting conversation this morning.